future. So I would like to introduce our speaker tonight. Arno is the founder and CTO of thinkcell. Arno is responsible for the design and architecture and the development of all thinkcell software products. He oversees thinkcell's R&D team, quality assurance, and customer care. Before founding thinkcell, Arno worked at Microsoft Research and McKinsey. Arno studied computer science and management and holds a Ph.D. from Georgia Institute of Technology with a specialization in computer graphics. Today, Arno will be talking about error handling, and his talk is titled A Practical Approach to Error Handling. So Arno, thank you, and I'll hand it over to you.
Thank you very much for the intro, and thank you very much for attending the talk. So yes, I will be talking about the practical approach to error handling. thinkcell is actually, just a short introduction, we are producing an add-on for PowerPoint, which doesn't sound terribly exciting, but we take great pride in writing really nice C++ code, and we have a large C++ library, and we try to basically learn how to write better code every day. And we are also involved in the C++ Standard Committee, and we are sponsoring the German delegation. So today we'll talk about error handling. And well, what's the problem here? Well, everyone has to handle errors. Errors can happen anywhere, and we all want reliable programs, but we have absolutely no time to write error handling. So what do we do? And this is going to be the question for tonight. What do we do? First of all, before we start discussing this question, let's talk a little bit about how errors can occur and how can they be reported to the program. So let's say you have a file and a file object, and it's opening a file like here. And this file is not there, and you have to somehow tell the caller, well, that file doesn't exist. How can you do that? Easy ways are, for example, return values. Return values don't work with constructors. So, and if you have a constructor, you can still use an out parameter, an extra parameter that gets filled. Both is not terribly elegant. You will clutter the code with checks, and you may forget to check. There is now in the newer C++ standards, there's no discard, so that you can try to, for at least for the return values, you can try to avoid the situation of forgetting the check, but still it clutters your code, not terribly pretty. Now, there's one good option that I want to bring to attention, which are error flags. So when you have an operation that only needs to be checked at the very end for completion, like writing to a file, then it's sometimes nice to say, well, just do all this operation, and at the very end, we'll check whether everything succeeded. Another example for that is, first of all, C++ IO streams use it for writing files in particular. But like graphics operations are also like that. When you're talking to the graphics card, you push all your triangles to the graphics card, and then at the very end, it may tell you, okay, that was all good, or it wasn't. That is good because you have only a single code path. You don't introduce extra code paths for the error handling. You can do all your operations in a single code path, and at the very end, you can check. Now, there is another approach that is geared towards having a single code path for the error and the success case, which are monads. They are kind of like a STID variant on steroids. You have a variant of the result that you would actually produce and a potential error, and you may have one of the two, and you may have some utilities that push this structure through your program. So when you return it, you can say, well, if that was a success, then do something, otherwise pass on the error. And so you pass this thing through your program, always following one code path for the result and the error to try to keep things simple. There was actually a C++ standard proposal, still expected, that is still making its way through the standard committee. So it hasn't been standardized yet, but it may actually happen. Now, the typical thing to use to report errors are, of course, exceptions. And before we go into the more intricacies, a few basic things about exceptions. You should always catch them by reference, otherwise they'll be sliced. So for example, here, if you have a structure A and you have another structure B that derives from A, and you're just catching A by value, not by reference, then the B will get sliced into the A. And that is problematic because B may contain interesting information. It may have some virtual functions and B may implement them in a different way. So you don't want slicing, as always. And then during the copying, you may actually invoke another exception because the copying may fail or because it has to allocate memory. And then you have a double exception and your program terminates, which is also not ideal. And finally, there's one other thing that I found interesting. If you write just throw semicolon, actually it will throw the original object. It will not throw the A that you caught, which is kind of surprising. So in general, just catch them by reference and then you'll be okay. Now, exceptions work a little bit like a multi-level return goto, which is a little bit a mean thing to say, but it is a fact that they add invisible code paths to the code. And that's the reason why some code bases don't allow exceptions. They don't want exceptions. So if you have something like this here, where there's an increment function that throws, if I is 3, and then there is a main that calls the increment function and then catches the exception, you could say, well, it's a little bit, here are the two things. It's a little bit like adding this extra escape path from your increment function, where you go to some place outside of your function and you transport this type of exception out with an out parameter with this extra channel that transports out the exception. And then upon return from that function, you check if that exception occurs, and then you go to your exception handler. So it's clear you get extra code paths. Now, people may say, well, stop whining. Of course, you must write exception safe code. Now, what does that mean to write exception safe code? Let's talk about exception safe code and exception safety guarantees. These guarantees are not really exception specific. It's more like what happens if a function fails. And they are really part of the function specification. A function should say if it can fail, and if it fails, how it behaves. Now, the best thing that a programmer could hope for is that a function just never fails. Now, sometimes this is probably not possible. So the next best thing is the strong exception guarantee. Strong exception guarantee means that if it fails, then it will restore the program to the state it was before. So it's transactional. Either you get everything or nothing. And that's certainly desirable and doable in library code. And there it's what we want. It's very hard in application code because usually when there's a longer operation, you're changing a lot of state in your program, and you would have to roll back that state in case of an error. And so you may have to remember all these state changes in order to cleanly roll them back. And it will also add quite a bit more code to your program. So it's just in general hard to do, or at least costly in terms of the amount of code you would have to write. Now, the next step down is the basic exception guarantee. So the program, the function may fail, and it will restore the program to a valid state, to some valid state. It won't crash the program, but it is not necessarily the state that you had before you called the function. Now, how useful is that? You can imagine someone calling Microsoft, hey, is this Word support? I'm writing a book and suddenly Word deleted everything. And Microsoft says, okay, that's fine, because Word has only the basic exception guarantee, and an empty document is a valid state. And then the customer says, yeah, that's fine. Now I understand. That's perfectly great. I'm happy now. Now, you're very unlikely to have that kind of conversation. So it is really doubtful whether the basic exception guarantee gets you very far. So now we are back to where we started. error handling is a lot of effort. In development, we have to be extremely paranoid. We have to check everything. We have to consider all possible things that may go wrong, and we have to handle all these things that may go wrong, which creates a lot of code. Now, this again will create also a lot of code paths. And in testing, we have to test these code paths, because if you don't test the code path won't work, as we all know. Now, what do we do? And on top of it, the customer says, I want to get my work done. There's no gain from you having these wonderful error dialogues that you wrote for me. I want your program to work. I pay for you to work and not to have wonderful error dialogues. So again, what do we do? So here's what we did at thinkcell. First of all, check everything. Every API call you do, you have to check. Basically, this boils down to have one wrapper per error reporting method. If Windows reports error with get last error or H result, you have a wrapper for get last error and H result. If Unix uses Arno, you have a wrapper for that. Now, you assert aggressively. So you constantly check, is everything making sense that's going on in my program? And we leave these asserts in release so that the program is checked on the customer side and not just when we are doing our tests. Now, all the functions which are not supposed to throw exceptions are marked no except. If the caller basically doesn't expect any exception here. If an exception is thrown, that will lead to st terminate. Yes. But if you have an unexpected exception, your program is probably going to crash anyway. So st terminate is not a whole lot worse. And we did install a handler again with st set terminate, so that when there is such a termination happening, you will actually find out, you will get a report. So this is about checking whether things are working. And we check everything. And then we assume that everything works. Nothing will go wrong. And the goal here is we keep the set of code paths small. We don't write code that we'll never need. We won't introduce program states that you may never need, that just complicate the code. By the way, if you want to ask questions, just type them into the window, into the chat window. And I mean, you can. Is there any way to keep asserts in release? Yes, there is. I mean, you just you can write your own assert functions. You don't need to use st assert. And we do. So it's just like these wrappers that you use for error reporting. You just have lots of functions which help you detect errors and generate meaningful reports. Okay, so what do you do if these checks fail? First of all, priority number one is not to make the program work. The program failed. Priority number one is to collect information. You want to fix the problem. So when it happens on the client, we send the report in Windows with a mini dump. That's fairly common. On Mac, we wrote our own piece of code, which I think is on GitHub if you look for thinkcell, our repository, there is something similar to a mini dump. So you just collect information. That's basically the local stack with local variable contents, and you send them home, send them to thinkcell. They get sent to thinkcell in our case. Now, that's when you're on the client. When you're on the server, you just hold the thread and you notify the operator. You say, hey, my server just did something weird. I'm going to stop here and look for someone to attach to the server and debug, because the best information about, remember, it's priority number one. You want to find information, you want to get information. The best debugging environment you will have is the actual server that has all the local variables, all the information you would need. Just stop it and wait for someone to attach. Now, priority number two is you carry on somehow. Now, if the check that failed was critical, which is the general assumption I basically made so far, then your program behavior from now on would be undefined. It's you don't really know what broke when you violated your assert, when your API call failed. So disable any further reports. There's no point in diagnosing a program that is already bad. You just get spurious reports that you're going to chase, and so disable them. Now, there's one more important thing. If an assertion fails, do not terminate. Don't do anything. Don't show an error message. Don't do anything. Because asserts can be wrong too. And if you make bad things happen when assertions fail, then the programmers, the developers in your team won't write assertions anymore. They'll stop writing assertions. And you don't want that. You want them to write really aggressive assertions that will keep the program on that narrow path of correctness that I was talking about. Now, if you need safety in your program, then add this safety at a higher level. We do this, for example, well, we don't have a nuclear power plant that we are controlling, but let's say you have the server thread, and the server threads are hanging, and I just told you when the server thread does something bad, we'll just stop the thread. Well, what now keeps our server from clogging up entirely? Well, you could say, okay, I'm going to divide up my requests in categories, like the different kind of requests I'm getting to the server. And there is a pool where I'm only allowing like a certain number per category of threads to enter. And when when I have 20 threads already hanging in one request, I'm just going to stop serving this kind of request. So when there's something badly wrong with the server, so that basically all these threads are hanging, you're just going to stop the server is unreliable or is not working for this type of request, but all the other types of requests will continue to work okay. So now, once you did all that, once you collected all this information, it's time for homework. You have to reproduce the error at home, and because the goal is you will only add handling code for errors that are reproducible, that you understand. Now, our experience shows, if you don't do that, if you just blindly say, oh, my telemetry tells me that this error is occurring, I'm just going to write an error handler for it. The chances are you're going to write error handlers that are never used because you didn't write them in the right way. And they're never really tested because you didn't really have the reproduction for the error. And there's one example. We used to use the XML reader component of Windows, and sometimes this XML reading failed. And you could have just reported, XML reading failed, but it turned out we tried to reproduce it, and we found some customer where it occurred. And it turned out the basically one reason why this was occurring was because the component wasn't registered in the registry. So our error handling was actually, okay, this error occurred. We are now going to register this component in the registry and then try the operation again. And that was 100% effective. It just stopped this error from occurring altogether. And this is kind of the error handlers you want, the ones that don't bother the user, the ones that really fix the problem. Now, if you do that, it turns out that 5% of the handlers handle 95% of the errors. So these errors are extremely clustered in very few places in the program. And these are the ones that are interesting. You may say, well, ideally you would like to handle all the errors, but I mean, we have to focus. We don't have infinite amount of time, an infinite amount of development resources. So we have to focus the resources where it matters. And so it's very important to just identify the places where it actually makes sense to handle errors, but then to do it there effectively, so the error doesn't bother your user anymore. Now, I want to go through categories of errors that can occur from the most severe to less severe errors. A critical error, undoubtedly, would be a null pointer access, or, for example, an API call that is not expected to fail, or maybe even it may be expected to fail, but with a particular error code, because this error handler will actually, well, may only accommodate a certain error situation and not everything. Failed assertions are also critical. They all are basically considered to never happen. So we don't write a handle for it, and we consider the program state after they occur to be invalid. It's a bit like C++ undefined behavior. From then on, basically your computer is on fire. And you can't make any assumptions about how the program will behave. In practice, it will often continue to run, but we're not going to change our code. We're not going to accommodate that in our code. Because that basically, if you start doing that, there is again the question, where do you stop? And it is enormously cleaning up the head, cleaning up your mind to say, okay, I'm just going to say this is just something that never happens. The client will send reports, send a report, gather information, send a report, and it will disable all future reports. Now, the server, as I said, will notify the operator and stop the thread, enter an infinite loop, and wait for the debugger to be attached. Now, the user will only be notified of this problem if a false alarm is unlikely. That's the thing with the asserts, that you don't want to report failed asserts because there you may have a false alarm. If you have a failed API call, a false alarm is much less likely because you are probably doing this API call for a reason. We actually don't notify the user if the API call is expected to fail, but with a different error code. And this is kind of like a matter of pragmatism, of hope, where you say, okay, I probably, maybe if I have some error handling, maybe it's okay, maybe it works. But this is all just pragmatic. This is all in your head. The program behavior is still undefined after a critical error. Now, there is another level of error that proved to be practical, which is it's basically it's defined behavior. It's defined in the program. You can carry on. You want to carry on. Nothing is going wrong in your code, but you've never seen this happening. Here's an example for that. Say you're running in a host application like we do, like PowerPoint, and there is it registers foo's. And whenever it registers a foo, you want to keep track of that foo that it registered. So you call the original, you put in a hook, you call the original register foo function, and if that function succeeds, and that's a call that PowerPoint did, in this case, the host application did. If that call succeeds, then you know now you have a foo to keep track of. So it's very easy to say, well, if this error succeeded, then we're gonna, if this call to register foo succeeded, then we'll keep track of foos. Now, if the error, if error indicates an error, right? If register foo failed, we have nothing to keep track of, and we could just return error. But let's say we've never seen the situation where register foo fails. Now, by the letter of the program, it would be okay to just check for an error and say, well, if you made a mistake registering a foo, then we're just not going to keep track of it because you didn't register anything. But maybe if that never happened and you never reproduced it, then maybe the rest of the program is not going to be very happy if suddenly this register foo is failing. So you may want to keep track of it, and if it would be interesting, it would be good to have a reproduction if such a reproduction occurs. So this kind of error is one where we still send a report. We will keep track of how many such reports we send, because if you are sending too many of them, the computer is just going to be busy sending reports. So we want to throttle that back once we send maybe half a dozen of them. And certainly when you're running a debug, you will certainly want to pop up something so that the developer knows, oh, I got a reproduction for this thing that I didn't know how to reproduce. Likewise, with the server, we are sending a report, but we'll continue running the server. But we now know that this thing actually occurs, and we have to hunt for a reproduction. Now, even more one further level down are bugs which are third-party bugs that you know that you have reproduced, and you don't want to work around them because they are maybe rare, and you want to focus your resources elsewhere. So let's say PowerPoint sometimes makes shapes disappear. Now it's reproducible, it's supported, and it's tested. So basically your application stays in well-defined behavior. It's all good. But the user is going to be unhappy because the PowerPoint shapes suddenly disappear. It's not your fault, but if it happens, probably people are going to call you and say, "Hey, my shapes are disappearing. Why does that happen?" And it's nice if you then could look into the log and say, "Oh yeah, you ran into the situation that we know occurs, and we've documented how it can occur. But we can now explain to you why it happens. And if it happens too often and we get all these calls, maybe we want to consider doing a workaround. But even there, we don't want to maybe do a workaround if it's really rare and people are not complaining." Okay. Even one more level down, there are indicators of broken environments. We are hooking some functions, and other add-ins may also hook functions, basically overwrite the function beginning to insert a little jump to the hook. And if everyone plays along nicely, then multiple people can hook this function and everything works. But if they don't, then things start to break. So that's why we kind of want to log if this actually happens. Or some other example would be the operating system reports space. It's an unusual decimal separator, and it's fully supported by the program, but maybe something else is going to behave bad, and then we want to know. Now, here, what we do is if we are in a remote support session, so if you are sitting with client and we're looking at his monitor, we set a flag that whenever such a situation occurs, we will pop up a notification so that the person who was doing the support call knows that this is an unusual environment. Now, since we've gone through all these lists of errors, I want to talk a little about and the approach to error handling. I want to talk a little bit about error analysis. So we collect all this information from these errors occurring on the client machines, and we get all this information sent to the server. And usually this happens automatically if the user agrees. But the user can also opt out, and then if he gets a notification, I have an error here, then he can actually send us an email and then basically decide to provide us with the information that we request to help finding the bug, finding the problem. Now, we put all these dumps or these reports into a database, and they can be opened in a debugger, so you can just double click them, and the local environment, the local variables will be available in the debugger of the error that occurred. And these errors are also automatically categorized by where they occur in the source code. And now the nice thing is that the developers can also mark these errors as fixed. So they can say, okay, from a certain version onwards, we fixed this problem. And this will actually trigger an automatic update. So when this error occurs and the report arrives, the automatic system can actually send back, I think this is fixed in this and that version, and we'll trigger an automatic update. Now, this also works with email, which is close to magic. So you can send us an email. People send us an email. There's an error, and in 5 seconds they get the answer back. This error is fixed in version XYZ. Please update. And when we introduced this, we got kind of surprised users because yeah, we are so quick answering emails. Now, you can also do something which is related to the finding the cause of the problem. When you're running production software, and especially when it's in a challenging environment or an environment that is hard to control, like a host application like PowerPoint, the problems are often related to the customer environment. It's not something that you've found during testing because you didn't have all these environments that are out there from the customer. Now, so is there a way we can actually find out what the problem is, what the environment problem is that the user has? Now, these memory dumps, they all have a list of loaded modules. They have a list of DLLs or dynamic libraries. And the question is, can we identify which module is causing the error, or which versions of a module are causing the error? Okay, let's see. So we have a database with all the reports, and we can use all the reports which don't have this particular problem that we are currently looking at, kind of as the background distribution of modules. And some of these reports will have the problem that we're looking at. And here you could say, okay, we have 12 reports in total, which have all kinds of errors, but 6 of these errors have the particular error that we are looking at. And then you get this, well, 0, 1 string of encoding, which basically report belongs to this error. Now, again, some of these reports are going to have, let's here for example, let's talk about 2 modules. Okay, and some of these reports will have module A, and others will have module B. And if you now look at the distribution of the module A among the things that have the error or that don't have the error, then you'll see that there are, with the error, you have 3 times the module, and 3 times you don't have the module. And without the error, you also have 3 times the error. Without the error, you have 3 times the module and 3 times you don't. So the distribution of the module A is obviously independent of the presence of the error. So module A probably has nothing to do with it. Now with module B, you have the error, you have the module more often, 4 times out of 6, when the error occurs, and only 2 times out of 6 when it doesn't occur. So module B may have to do something with the problem. And it would be interesting if there is basically a scientific, a solid, sound way to say, is this chance? Or is this something that we should actually look at? And I'll show you one way to do this. So we are going to do minimum description length, essentially looking at encoding this report stream, this stream of 0 and 1s, whether the error occurs or not, based on the knowledge whether a particular module is present. So if basically if we know that a particular module is causing the error, then of course knowing that this module is present will be a great predictor for the occurrence of the error. And it should help us compressing the string of 0 and 1s, which indicate whether the error occurs or not, because the 1s will be associated with module B being present. So we are going to use perfect arithmetic compression, Laplacian estimator, and we'll estimate the probability P that the report has a particular problem. And given that module B is present, or module B is not present. Now, we consider all the P's equally likely in the beginning. And then when we have to compress n bits, and we have k ones, then it's the number of bits that we need to compress them is this n plus 1 times n over k, and the logarithm of it. And when the number of bits that we need will actually become smaller if p is closer to 0 or 1. So if you have 12 bits and we have to encode 6 ones, then we need 13.55 bits. And for 12 bits with no ones, we need 3.7 bits. Now you may ask, well, 12 bits with 6 ones, I can obviously encode this in 12 bits. Yes, you can, but then you will make no use of the fact, you will not learn that P is much, much closer to 0 or much closer to 1, and then you might need much fewer bits to encode the stream. So here we are kind of assuming that we have to learn the distribution while we go along encoding bits. And that extra information will cost us a little bit. And that's where these 1.55 bits come from. But the advantage is that if P is close to 0 or 1, then we need much fewer bits than the 12. Now, we can compress reports. One with basically the first compression we're going to do is we can compress all these reports together. We basically learn how frequent is the report in the whole set, or is the problem in the whole set of reports. And that determines then the number of bits that we need to encode in which reports that problem occurs. And that does not consider at all whether there's any module present or not. Now, that's basically one option. We say no module is responsible. We have no idea which module is responsible. Now we can say, okay, let's assume that module A is responsible, and we need to encode this. We need to transmit this information. I'm telling you now, module A is responsible, and the receiver is assumed to know in which reports is module A. So they will know that, okay, I now have to take a good look at which reports have module A and use different distributions for those with module A versus those with module B, that don't have module A. So compressing all these reports with A, which are 3 out of 6 have ones, costs us then 7.13 bits, and all the ones without also 7.13 bits. And not surprisingly, the total 15.26 will be higher than the 30.55. So basically, you told me that module A has something to do with it, but that didn't really help me compressing any better, because in fact, it doesn't have anything to do with it. So I would just have to learn my distribution twice, which costs me more bits. Now, if you're then doing the same with module B, then, well, the statistics should be better, right? Because we were kind of saying that it occurs 4 out of 6 times. But here it turns out, if you do the math, it still needs more bits to transmit the fact whether the report has the error or not. If you are making it conditional on the presence of module B. So here, since the number of bits is higher that you need, it's still not relevant enough. It's not enough to say, okay, it's probably module B. Now, let's say we have a module C, and now if we have an extra module C, which is 5 out of 6 and 1 out of 6, so it's really like very much associated with the report, with the problem. Now it works out well. So first of all, we have to choose module C over A and B, which requires us to choose 3, make a 1 out of 3 choice, which requires more bits. But then when we compress the reports where 5 out of 6 have the problem or 1 out of 6 have a problem, we save so much that at the end we come out ahead. We can actually compress better. And in this case, we would say module C is probably responsible for the error. Now, you can do this for first of all, many more modules. And of course, the more modules you add, the more hypotheses you add, the more likely chance is going to be. And the more significant the module has to be a good predictor to basically be worth considering. I mean, if you're doing just enough chance experiments, something is going to appear significant, although it's just a chance if you just do enough of these experiments. Now, you may also extend it to module versions, and it actually also works if a certain module fixes the problem. You don't need to do anything special. It just works out that if basically the non-presence of a problem non-presence of a module fixes the error, it will just tell you that just as well. Okay, now I'm coming to the end of the talk. I want to talk briefly about C++ contracts. They are a new language feature. It's essentially an assert on steroids, and they will let us declare function pre and post conditions. But, oops, yep. There are a few questions still. When should you check a precondition, post condition in debug, release? Maybe never. Maybe it's just for documentation. And what do you do if you violate a contract? I showed you, I talked about all this machinery that you can basically build for failed assertions and for failed API calls. And so you would have to specify, well, what should actually happen if such a contract is violated? You could terminate, carry on, and report. And since there were so many questions, it got removed from C++20, and there is still this discussion continuing for C++23, where hopefully we have contracts and hopefully with enough customization points that you can also implement meaningful reporting. All right, that was the talk. Thank you very much for attending. And yes, we are recruiting. So hr@thinkcell.com if you want to send the resume. And now if you have questions, just go ahead.
Thank you, Arno. Yeah, we'll just open up for questions now. So feel free to unmute yourself if you have a question.
Okay. All right. Can you give an example of when you would carry on versus just restarting? I'm thinking you have a failure, you know that you're in a bad state, so carrying on is just going to propagate the error state.
In an assertion, it's actually quite frequent. People write just aggressive assertions. They say, okay, my program state has to be this and this at this particular place. It may not be the direct precondition of the function, just the way that the function is used and the way they think the program states work and the program works, this assertion should hold. And they kind of, in their mind, they have that idea that's how it should be. And then certainly you want to encourage them to write that into the code, that assumption. And then it's actually quite frequent that these assertions don't hold, but the program still works. It'll just be okay. It's like, oh yeah, I was a bit too aggressive and I forgot about this one case. And yeah, but I can just, relax the assert a little bit and then it'll be fine. So if you want to get really, aggressive asserts, then you probably have to carry on.
Then the problem is it the assert or is it the code?
Well, I mean, you want to give people, yes, right. I mean, it may as well be the code. I mean, certainly. I mean, you're not going to fix an assert by just removing it. But if it's, if that's the right thing to do, then you do that. And if you have to fix the code, you fix the code. But it's not a situation that is so rare that you could afford, say, terminating a program just because an assertion failed. I think that was discourage people from writing these aggressive asserts, and that's really we don't want that. It's very valuable to have especially with this database of reports. It's quite frequent that you see an assert in the program and you wonder, okay, that's good to know that the situation is restricted to this particular set. Let's look into the database, see if that's really true. And usually the answer is yes. There's like out of gazillion reports we receive, or millions of reports, there's not a single time where that assertion failed. And you can say, yeah, it's basically we proved it to be true without, maybe without fully understanding it. You probably should understand it, but I mean, empirically, you can also say, yeah, this was never violated.
So would it be fair to say you kind of have two levels of asserts? You have hard asserts and soft asserts, where the hard asserts are like, I'm going to die now, and soft are saying, this is something we want to record for future examination.
Maybe if you put, I didn't want to put that burden on the developer to make that decision. I think that's what it boils down to. If you feel differently, I think feel free to make a different decision. I think that's fine. I think there should be a level that doesn't terminate. And if you think there should be a level that does terminate, I mean, certainly that certainly, and it very much depends on, maybe also what you're doing. But yeah, my main point here is that there should be an assertion that is relaxed enough so that people can afford to make mistakes without disrupting the running the program.
Thanks.
Hello.
Hi Arno, Matthias here. Thanks for the talk. I was wondering, you're shipping with certs enabled, so what's your take on also shipping with certain sanitizers enabled, which I guess is some kind of additional asserts you could add to your code?
So far, the sanitizers we ran, like memory sanitizer, for example, were just too slow. It was not practical to do. That's the main thing. I mean, all the sanitizers we've seen so far are so intrusive that you can't afford running them in release. And yeah, and otherwise, I mean, yeah, sure. I mean, whatever you can afford, you can do. But we have enough like performance critical stuff that that we can't do that.
I think Armin had a question too.
Yes. Do you limit the size of error reports? I mean, sometimes logs or some other information may be very big, and do you cut it to some size or maybe filter in some way?
Yes, you can. Yes, you can do that. It's relatively straightforward because these mini dumps contain the big part they contain are the local stack, and or actually all the stacks of all the threads, and you can always decide like what the stack depth is you want to transmit, and you can always cut it off, and you say, okay, I'm not going to do the whole stack. I'm just going to stop like that many levels down. And you can control that so that you have a certain target size of your mini dumps, and you just pick the stack depth accordingly.
Thanks. On my work, for example, we cut the log to some size. And what do you think? What do you prefer? Because sometimes cutting the logs may cut off some significant data, for example.
Mm-hmm. We don't transmit any logs. I mean, not by default. Not if someone. I mean, we do log to the local disk, but that's only when we actually when the user is actually sending us an email that we'll include the logs. The automatic report is just the mini dump. It's just the local information, because I guess also our logging is not really. It's especially when you're running a release, comprehensive logging would also be probably too slow. So we don't log much in regular use, in like regular operation.
Thanks.
One more question from me. Debugging optimized applications can be pretty hard, even if you have a good dump. Do you have some things you employ there to make this easier, especially like variables that have been optimized out or code that has been heavily reorganized by the optimizer?
No, I think the simple answer is no. We fully optimize the program, which is particularly important because these all that debugging code that we put in, all these assertions, and also our library requires just very aggressive inlining. Without aggressive inlining, in debug our code is really slow. So really disabling optimizations are not really an option, and we haven't done it selectively. Maybe we could. It's not been such a pressing problem, I guess, is the answer. But yeah, if it is a pressing problem, then we would have to come up with something where you would have to restrict optimization.
So we have a question from Samuel.
Yes, first, thanks for the talk. That was really interesting. I have two questions. I'm curious to know how do you approach like this whole idea of having really aggressive assertions when you're inside of a performance critical loop or hot path? Like, do you do the same thing, or do you have like special techniques or way of doing things that you only like?
I try to. I mean, we try to. We usually put in assertions just even in performance critical code, And then it's kind of part of the optimization to take them out. So we profile. Essentially, if this stuff appears in the profiler and we see that it's on a hot path, then we say, okay, we have to make this an assert debug. If it's really bad, we sometimes have two functions, one for the hot path and one for the slow one. So basically, we selectively just run the non-asserted version of the code in these very hot paths. And otherwise we use the cold ones or the asserted ones for the cold paths. This is something that does happen, that we are basically running a profiler and it's like, oh, we have to make this and debug only assertion, for example. We can't ship this assertion because otherwise it will be too slow. But it doesn't happen terribly much. It's usually the inner library code where that would happen. And there we do these workarounds.
Thank you for this answer. And my second question was, like, I imagine that if this is like the only technique that you use to do error handling, you must be checking, you must be pre-validating a lot of conditions before you actually launch any functions. Let's say like you don't throw like any argument into your constructor. You must be.
Oh no. I think this is I think maybe that's it's a misunderstanding. So we use all kinds of error reporting mechanisms in the code. Still, we use return values, we use exceptions, we use all that stuff is still there. It's just only it's not. We just distinguish between very much or very strongly between basically defined behavior. So these are things that we handle, and we can handle them with every means available to C++, whether that's exceptions, whether that's return values, whatever you have, that's monads, or it's undefined behavior. And if it's undefined behavior, we don't handle it, and we just make this distinction very strongly. And it's basically really black and white, and during code reviews, developers are really encouraged to say, okay, this is what we support, and this is what we don't support, and yeah, so it's not like we're not writing, we're not using exceptions or something like that. We do all that just like the normal code. Just it's all that is not really considered an error. It's considered regular program flow.
Thank you.
All right, do we have any additional questions? You can use the, I forgot about the raise hand under the reactions. You can, if you want to do it that way, I can call your name. All right. Well, great. Well, thank you, Arno. Everyone, I would give Arno a nice virtual applause. Thank you for coming to our meetup and giving this talk. I'll just say a few closing remarks here. So, again, as we announced at the beginning of the talk, CPP North is our planned conference in 2022. Please visit the website for some more details of where the conference location is going to be, and follow us on Twitter. We are also beginning our search for sponsors, so please reach out if your company would be interested in sponsoring. There's dedicated sponsor links on the website, so you can reach us at. Also, we're continuing our virtual presence here. We have a next event coming up soon. I don't know if we've announced it yet. Have we, Mike? No, we have not announced it yet. So please stay tuned for that. That'll be coming soon. And if you're interested in speaking at a future C++ Toronto event, please contact us. We're always looking for speakers. And if you need help putting together a proposal or presentation, there are many people on the Include C++ Discord who will be willing to help you, which also I'm going to put a plug in for the Include C++ Discord. If you're not there, I would highly recommend joining that Discord channel. And so finally, If you are looking to hire someone, please put a thumbs up in your reaction. And if you are looking to be hired, use the clapping emoji. You're limited emojis here on Zoom, so we'll have to use what we have here. But and feel free to exchange contact details on the chat. We'll leave things open here for a little while longer. Yeah, thank you everyone for coming.
Thank you very much for having me.